So we've talked in the past about internal forces. As we get going in strengths and materials, we're really not going to be successful figuring out the stresses or the deflections unless we can predict what those internal force values are. So we want to spend some time going through this, essentially reviewing from our work in statics. If you remember back to what we did in statics, we had a three-step method. Engineers tend to like stepwise methods, so here's the three-step method. And as we get into these problems, some are going to be so easy, you'll think, oh, I don't need this three-step method. But then as we get into the more difficult problems, particularly the transverse problems, the beam problems, the three-step method should serve us well. So we'll practice it in the easy problems so that we can hopefully succeed in the more difficult problems. So the process is we want to, one, draw a free body diagram of the whole thing and solve for support reactions. There's a few odd cases where maybe we could skip that step, but usually, and certainly as we're just starting out, we want to solve for the support reactions. And then the second one is a free body diagram of each section where the load changes and solve for the internal forces. And with this one is where we're going to have to put the internal forces in the right direction. And that leads us into the deformation sign convention. You might say, well, I could cut it apart and put those assumed internal forces in either direction and would just let the negative signs take care of themselves. And that's true, but then your diagram may not look like my diagram or look like the author's diagram, and we want our diagrams to be consistent. So we've sat down and come up with what we call the deformation sign convention. If I have an axial load and I slice through the thing, if I'm looking at the left-hand side, I draw this axial tension load. The axial tension load like that. If it's a torsional load, remember I use the right-hand rule. You take your right hand and you put it in the direction of the torque, and your thumb then points in the direction of the double arrow. These are double arrows. So this would be the internal torque Q. Okay. And then the transverse load, that gives way to internal shear and internal bending. So that's the shear is the forces and the bending is the moment. So whenever we cut through something, if we're going to cut through something and have the left-hand side, we're always going to draw it like that. If it's a torsional problem and we want to look at the right-hand side, we would draw it like that, and so forth. Those conventions are unfortunately something you just have to memorize, and that's so that when we get done with the graph, when we get done with the plot, that yours looks like mine, looks like the author's. And finally then, if we've done this right, we can plot this and we will be able to interpret the plot. We can make conclusions. We can say, well, if we want to save weight here, we could reduce the size of this thing because there's less load in this portion, or there's more load in that portion. So that's what we can do with that plot. Are there any questions then as we go into an example of this? Let's see what we can do. So I'll look at a axial example then. Let's say the axial example looks like this. We'll take and put a 3 kip. And remember that a kip is just equal to 1,000 pounds. Structural engineers deal in very large forces, so a lot of times they'll gather them up. So we'd have 3,000 pounds there, 3 kips. And at some point here, maybe we'll say that this is L over 2 and L over 2. So at the midpoint, we'll apply 7 kips. Okay, and we'd like to come up with the internal load for that. And I think a lot of you could probably step back from it and say, well, I can come up with the internal load for the first half and for the second half just by inspection. And that'd be fine. But let's practice this process on this easy problem so we can apply it to the difficult problems to come. So step number 1 is to draw a free body diagram of the entire thing to come up with the support reaction. So I'll take my support reaction here. Maybe I'll call that R. I'm going to have 7 kips here. I'll have 3 kips here. And if I sum the forces in the horizontal direction here, setting it equal to 0. That's kind of nice, setting that equal to 0 after dynamics, isn't it? Yeah, you don't have to worry about accelerations and things like that. So, and that's probably worth mentioning. I mean, I put free body diagram here. This is huge. That's why you got to have statics to take this class. We're going to use free body diagrams a lot. So don't forget those and don't forget to use them. So if I look at the forces in the horizontal direction, I'll take a positive to the right. So I will have 7 plus 3 minus R. Of course, R then turns out to be 10 kips, as you would expect. So now what I'm going to do is I'm going to go to step number 2, and step number 2 says that I'm going to take a section there and there. I need to take a section somewhere between the left-hand side and where the 7 kips is applied, and then somewhere between where the 7 kips is applied and where the 3 kips is applied. So I'll talk about then step number 2. Maybe I could say step number 2 I'll do right here. And I'm going to talk about X starting at the left-hand side and going to the right-hand side. So X is going to be between 0 and L over 2. So if I look at that, if it's between 0 and L over 2, I'm going to draw this left-hand side. I'll know that I solved this. This is 10 kips. And my deformation sign convention says that I need to put this internal tension in like that, right? Okay. So I came over here, I used this one. I used the left-hand side because I drew it from the left-hand side. I'll draw it like that, where this distance again is X. So if I sum the forces in the horizontal direction here, setting that equal to 0, I have T minus 10, or T is equal to 10 kips. Now I also have to do the other part, where I look at X between L over 2 and L. So if I do that one, and I could do this a couple different ways. Maybe I will continue on from the left side. So I'll take something that looks like this. We would have 10 kips here. I would have 7 kips here. This distance is still, of course, X, and I have the internal force T. I'm still drawing the left-hand side, so that tension force is going to go to the right. So if I sum the forces in the horizontal direction here, setting that equal to 0, what do I have? I have T plus 7 minus 10, so T turns out to be equal to 3 kips, doesn't it? Okay. And that's fine, and a lot of you will probably pursue it happily that way. That's okay. Another possibility, of course, here, so I'll put or. You probably wouldn't have to do both of these unless you wanted to check your work or something. But we could, if we wanted to, look at the right-hand side. So I come over here and I look at the right-hand side of this thing. And I have 3 kips. And I have the internal tension. Now I need to draw it that way, because that's what my deformation sign convention. I am now looking at this piece, right? And the only thing, and it doesn't make a lot of difference here, but when we start looking at distributed loads, it's going to make a huge difference. This distance here is now what? It can't be X, because I already said this was X, right? So this has to be L minus X, doesn't it? Okay, we can't have X coming from 2 directions. That's not going to factor into this necessarily, but it's something important for us to think about in the future. Well, if I sum the forces in the horizontal direction here, setting that equal to 0, I have 3 minus T, or T is equal to 3 kips. We get the same answer. That's good. Okay. So whether you look at it from the right-hand side or the left-hand side, you should get the same answer. Could you go from the right-hand side for this first half? Yeah, you could if you wanted to, but it's probably harder to do. So let's finish this up with the space that I have left, and I'm going to go to step number 3, which is a plot of this thing. So I'll put the X dimension here on the horizontal. I don't think I have units for that, so I'll just leave it as X. It would be 0 and L over 2, and then L. And I will have then the internal tension here in units of kips. So what do we have for the first piece? It's 10, right? So I'll have something like that. And then what's it drop down to? 3? So that's my diagram. Okay. So now that we have that diagram in mind, and again, I realize a lot of you probably could have sketched that diagram out from the get-go, but we want to practice this process. Once I have that diagram at hand, if someone wants to come in here and drill a hole in this thing, where would we suggest the hole? In this region here or this region there? The second one, there's a lot less load. Yeah, all things being equal. We'll talk later about stress concentrations and whatnot, something to think about. But just looking at those two pieces, we'd want it on the right-hand side. Or maybe we would want to build this thing like this. We'd want to step this thing down. And this is where you as an engineer have to start to think, well, is it worth that? If we're going to put it on the side of some ocean-going barge, it's probably not worth reducing the cross-section. If we're going to put it where it costs, several $1,000s to put a pound into space, then it's probably worth going through that machining process and whatnot. But that brings problems of its own. We'd have to probably put some sort of radius in there, or we're going to have a tremendous stress concentration and whatnot. So these are all things that we will have to deal with, but unless we have something like this, we're kind of shooting in the dark. Questions with that? Let's try another axial problem. So let's try one where maybe we have something hanging under its own weight. We'll take this as, we'll say we have 100 pounds acting down here. We'll say that this is 20 feet, and we'll say that there is a load on this, its own weight possibly, maybe something added to it, that is 50 pounds per foot. Okay. Well, I tend to always draw these diagrams in the horizontal, so even though this might be a gravity load, I think I will rotate this thing as I go through this process. So if I rotate this, I'm going to have 100 pounds here, and I'm going to have this 50 pounds per foot. And I'm going to have this reaction there, and we know that this is 20 feet. Incidentally, this is also, we'll take x at the top or at the left-hand side and say x is going that way. So if I sum the forces in the horizontal direction, which was the vertical direction, maybe I'll sum them in the x direction, setting that equal to 0, I could say that I have what? 100 plus 50 times 20 minus r, right? So r turns out to be 100 plus 50 times 20. What's that, 1,000? Is that right? Okay, so we have 1,100 pounds. That's what that reaction is. So there's step number one. Now, step number two, switch pens here. So step number two is I'm going to have to take a section through here. And we could start taking an infinite number of sections because this is continuing to change. But I think I'll just take one section and say we're taking that section at x. So I'm going to say that x is somewhere between 0, which would be right here. X is equal to 0. And x is equal to 20. And when I look at that section, I'm going to have something that looks like this. We found this reaction to be 1,100 pounds. We'll have our internal tension according to the deformation sign convention like that. This distance is x. And I still have this distributed load right there, 50 pounds per foot. So if I sum the forces on this, sum of the forces in the x direction is equal to 0, I would have t plus 50x minus 1,100. So t is going to be equal to 1,100 minus 50x. Does that make sense? Let's see. When x is equal to 0, we get 1,100. That makes sense. When x is equal to 20, we get 100. I think that hopefully makes sense. Now we could, if we wanted to, and again I'll say or, probably wouldn't have to do both of these unless we wanted to check our work or play around with it a little. We could do the right-hand side. So here I have the tension, no, I don't have the tension T. I have what, 100? So there's 100 pounds. And then I still have this, 50 pounds per foot. And the big thing here is that this dimension is no longer x, it's L minus x, or 20 minus x, isn't it? That's what that distance is. And I need to put this force in there according to the deformation sign convention. So when I sum the forces here in the x direction, setting that equal to 0, what do I have? 100 plus 50 times the distance, 20 minus x minus t. So t is equal to 100 plus 50 times 20 minus 50x. So I think that's 1100 minus 50x. So you can get it both directions. The one thing that's kind of interesting about this one is, did I ever need to find the reaction for this one? Yeah, no need for R. So when you get really good at this, you'll start to think, well, if I come to it from this direction, I don't even need to find the reaction on the thing. Okay, now I don't know that that's a really good thing, because when we go to step number 3 and draw the picture, here is x in feet, 0, 20, and then we have the t in pounds. For the when it's at 0, we're going to be at what, 1100? Having found that reaction to be 1100, that number is quite a bit more satisfying, right? Okay, if I didn't know that, I'd probably be a little more worried. But since I know the reaction is 1100, I like it that that equation hits there. So I don't think there is anything wrong with doing it this way. Finding that reaction is kind of a nice check through this process. Yes?
For that second one, after we find the equation of tension, can you set x equal to 0 of the reaction?
You could, although you're not necessarily doing an independent evaluation when you do that. I mean, this process here was more independent than just putting x equal to 0 to find the reaction. Okay. Well, that's a good point, but it's probably not as thorough a check as doing this. So let's see, if we look at x is equal to 20, we come down to 100, is that right? And it's a linear equation, a first order equation, so I should have something that looks like that, right? Okay. So this is where, I mean, if you model this as some unruly child in the Oregon Caves National Monument hanging on a stalactite. Okay. I'm not sure how I can draw a child hanging without getting in trouble here. But anyway, you got the shape of the stalactite is pretty well designed for this, right? The higher load is up here, the thicker area is up here, the lower load is down here, the thinner area is there, isn't it? Yeah, well designed. Questions with that? Well, let's look at torsional problems then. So with torsional, we see these in a variety of different places. If you look at maybe an extension on a socket set, you've got some sort of a that's not much of an extension. That's a real cheap import there. As you apply a torque here and you have a resisting torque there, you're going to get some sort of a torsional loading, right? Maybe it'd be a little easier to see on a screwdriver, the shaft of a screwdriver. Okay, and as we apply some torque here, and you have some resisting torque from the screw, like that. And before we totally disenfranchise, I mean, well, I guess we could do the classic example of the drive shaft here. You have the drive shaft, whether it's front wheel drive or rear wheel drive. There's the hooks joint or the universal joint, the cross. Maybe you have a spline section here, so it'll slide back and forth. And then you've got this going to a cross here. Okay. And if you're applying some torque here, and you have some resisting torque here, if you were to look here, or here, or here, you would have internal torsional loads, wouldn't you? Okay. And before we totally disenfranchise our civil friends, I mean, this comes up in civil engineering too. It's not just mechanical components here. It's probably a little easier to see in mechanical components. Well, let's say that we take a sign. Maybe we have a property line issue or an easement issue or something like that. So our signpost has to be a little bit odd. So we put this signpost here in a footing. And then this sign, this rigid sign, has to stick out like that. Okay, this happens all the time. You have an easement here or something. You can't put a post in it, so you have to do something like this. Well, this sign's probably got some dead load, right? And that's going to cause a moment this way, along with an axial load in there. But as the wind blows on this sign, what's that going to do in a section here? It's going to have a torsional load, just like the drive shaft or the screwdriver, right? Yeah, so civil engineers get into this. So if I take any one of these sections, I could look at them and draw them, and they'd look probably something like this. They might be going a different direction, but basically they would have one torque here, and then they would have a torque here. And it always gets a little bit difficult. Is which way is that going? Do I close one eye and squint the other? I got the wrong eye closed. How can I get that? So we go from this, and we use the right hand rule, and we can draw this in a more two-dimensional figure that's a lot easier to draw. So you take your fingers of your right hand and you put those in the direction of this torque. So that's going that way, so you'd end up with a double arrow here. So the direction your thumb ends up, so you take your fingers and wrap it around like that, and your thumb is now pointing in that direction. And then this one over here, you take fingers of your right hand and wrap it around there, and your thumb is then pointing in that direction. So we would draw a double arrow there, and we would have those torques there. So that's probably a lot easier to interpret. We don't have to try and figure out which direction things are going so much using that right-hand rule. It's also quite a bit easier to analyze because I don't want to propose heresy, but you could really treat this like an axially loaded problem now for mathematical calculations, and we'll look at that. Any questions with the right-hand rule? Everyone's good? Make sure you use your right hand if you're right-handed. So let's try a problem then. So let's say that we have some sort of a shaft coming out of a support, and I have applied a torque here of 100 pound-feet, and I've applied a torque to the end, representing it with the right-hand rule, of 200 pound-feet. Okay? And we'd like to come up with the internal forces. What's the internal force in the first half? What's the internal force in the second half? We'll assume that this is loaded at the halfway point, L over 2 and L over 2. Okay. So we're going to go through exactly the same process. Remember, our deformation sign convention looks very much like the axial convention. I'll pull that out here. Other than the double arrows, it looked exactly like the axial. If you're going to draw the left-hand side, it went to the right. If you're going to draw the right-hand side, it went to the left. So first thing is I need to find the reaction for this thing. So I have 100 pound-feet and 200 pound-feet. And then I have this reaction here. I guess I'll call it R, or maybe RT, the reaction torque. Maybe that'd be a little bit better. And this gets a little difficult. I mean, we can kind of shortcut it, but I mean, what you really have to think about doing is you end up having to think about coming down here and looking at it from that direction. And let's say that's a circular shaft, and we'd have this 200 that would be, let's see, that's coming out. So this 200 is going like that. Is that right? And then the 100 is in the same direction. I guess I just need one big arrow there and one big arrow there. There's 100. And then this one is going to be going in the opposite direction, so that's your R, or your reaction torque, isn't it? Okay. So if we really sum the moments about the center line of this thing, setting that equal to 0, I would have that the R sub t is equal to 100 plus 200, or is equal to 300 pound-feet. Okay. Now, a lot of you probably would have said, well, I can just do that as if I take 200 to the right and 100 to the right, that means that I would have to have 300 to the left, or that I could say that RT is equal to 300 pound-feet. And that's where I said, again, I don't want to commit heresy here, but you could almost think of this as an axial problem with these weird double-headed arrows, right? It's not an axial problem, but the accounting is exactly the same. This is what's really going on. You have those torques around that shaft, but you can add them up just like an axial problem. Well, I'm going to go ahead and take a section then through here. I'll take X starting at the left-hand side. I'll take a section here in the first half, and I'll take a section in the second half. So I'm going to look at X between 0 and L over 2. We'll look at something like this, where we have this internal torque Q, and I have my reaction torque that I found to be 300 pound-feet. And then maybe I'll do this again for X between L over 2 and L. And I could, I'll probably just come from the right-hand side. That might make it a little faster. So I've got the Q there. We've got 200 pound-feet. And I have to be careful. This dimension is X, whereas this dimension here is L minus X. It's not going to affect our calculations, but we always want to keep that in mind. It's usually a bigger deal when you have a distributed load. You could have distributed torques. Great application of distributed torques would be like an auger or something that's moving material along. It tends to increase its torque as it goes. To some extent, a camshaft or a crankshaft, as you apply load to it at each journal or lobe, has a distributed load on it. Well, if I were to go through the process either this way, looking at the end of it and summing up the moments, or if I were to just say, well, if I have this 300 going this way, then Q would have to be 300 pound-feet. And here, if I have 200, then Q is going to have to be what? 200 pound-feet, right? Just looking at simple accounting there, 200 to the right, so I'd have to have 200 to the left, 300 to the left, so I have to have 200 or 300 to the right. So in the first region here, I know I have 300. In the second region, I have 200. So when I go to plot this thing, here is X, and here's our torque in pound-feet. And we have, for a while, 300. And then at L over 2, it drops down to 200. So we have something like that. So if we're expecting failure in this problem, all things being equal, where would our failure occur? Probably somewhere in here, right? Somewhere in this region, we'd expect failure. Probably here. Oftentimes your attachments, you end up with failure. So it's a little bit like a camshaft or a crankshaft. Oftentimes if the crank fails, we would expect it to fail at the back where the power is coming out of the engine, right? Unfortunately, that's not where it usually fails. Oftentimes it fails close to the front because of vibration. So that's where the vibration dampener is. But if we didn't have to worry about pesky things like vibration, we would expect it usually to fail closer to the back. Questions with that? No questions? Mechanicals will go on and talk a lot about vibrations. Vibration can be a huge problem. I don't know, do we have any airplane history buffs, radial engines? The number of cylinders in radial engines, are they always odd or even? This will give you something to Wikipedia and Google. Yeah. The number of cylinders in a radial engine are always odd or even. Figure that out, and then why. So that'll give you something to mess around with. Questions on that problem? So that's a torsional problem. Fairly easy once you understand the right-hand rule. Let's go into transverse loading. This is where we're going to have to spend a lot of time because this is not easy. But you can make lots of money with this. So when people come and want you to design a beam, to figure out whether the beam's going to fail, you always got to have a sense of what the internal loads are. And that sense starts with coming up with a proper shear and moment diagram for this. So when you think about transverse loads, that can come in a variety of different cases. Maybe if we have a cantilevered beam, you could have a concentrated load on it. You could even have a concentrated moment. You could have a distributed load on it. It could be a simply supported beam that has all of these fun things, a concentrated moment, distributed load, concentrated load, or you could even have a simply supported beam that has a cantilevered section. Okay, all of those situations give us transverse loads. And there's two types of loads that come out of this. There are shear, and there are bending. Bending moment, and actually shear force. And we use the obvious symbol V for shear force and M for bending moment. So I guess M for bending moment makes some sense. So if we talk a little bit about shear and moment to give you some idea what these are. So you could go through the accounting of this not really understanding that, but I think it's probably valuable to have some understanding of what these are. Let's say that we take a really short cantilevered beam. So we look at a cantilevered beam like this, and we apply a very large load to this. So we have some very large load on that. And you could imagine that this might possibly fail. One failure mode for this might be that it would fail through this section like this. It would actually shear through right there. The Kansas City Skywalk disaster, worst structural failure in U.S. history, was actually a problem very much like this. A section of beam failed in shear, very much like this. Okay, so that's going to fail in shear. Okay, and if you want to think about this and maybe something that you've done before, if you take a piece of paper and you want to cut it, you can take some scissors. And what's another name for scissors? Yeah, you could call them shears, like this. And as you push these through that, it actually shears through the paper, doesn't it? Okay. Now, if your shears get a little bit worn out and get too far apart, so your shears look something like this, what happens? Paper bends through there, doesn't it? So in this case, we're going to expect the paper to fail in shear, aren't we? Whereas the paper in that case fails in bending, which is quite frustrating if you're trying to cut out paper dolls or something. Okay? Questions with that? Okay. So that's shear. This notion of bending, this is what happens in let's say, a much longer cantilevered beam. So if we take an example of a very long cantilevered beam, and it's probably easier to see in a cantilevered beam. We could make the same arguments for a simply supported beam. Let's say I put some load out here, and when this starts to fail, it's probably going to look like this. It's going to deform down. We'd have this load here. We'd start to have some buckling on the bottom and probably some tearing on the top. We'd end up with a lot of tension up there, a lot of compression there, and it would be failing in bending. Okay? A lot like our paper, when the scissors were too far apart, when the shears were too far apart, failed in bending. Questions with that? Well, our deformation sign convention is probably worth practicing again, is if you come to one of these beams, let's say that you cut through this, and you want to draw it, and you want to draw the left-hand side, or you want to draw the right-hand side. Your shear is going to act down here, and your moment is going to act counterclockwise. Or here, your shear is going to be acting up, and your moment is going to be acting clockwise. And if you think about pulling these two together, putting these two pieces back together, do those cancel out? Yeah, absolutely they do, and they should. Okay? So if we're going to approach it from the left-hand side, we'll be drawing this one. If we're going to approach it from the right-hand side, we'll be drawing that one. And that's unfortunately one of those things you just have to memorize. Questions with that? So let's try our three-step method, on a problem here. We'll take a very classic. Yeah, the six-step method is from, what, electrical, right? Anyone have a flashback there? Sorry. Okay. So I'm going to take a classic example where I have some concentrated load P, and it's located at the center here, L over 2 on that direction and L over 2 on that direction. This comes up quite often, whether you're to throw a plank up over some sawhorses and stand in the middle to paint something, or whether you're going to build an engine hoist, a gantry crane, or something like this. Is a very common problem that comes up. So I'd like to deal with it. And the first step is to find the reactions. And we'll very soon talk about a shortcut method. If you remember back a few weeks or months ago, you can probably remember that. But the shortcut method did not allow us to avoid finding the reactions. So finding the reactions is very important. So I'll say that I have a couple of forces there. I have a force here. I'm going to call this R1. I'm going to call this R2. I will say that... I guess maybe I'd better call this R3. We'll deal with that in a little bit. There's the P, L over 2, and L over 2. So if I look at summing the forces in the horizontal direction, setting that equal to 0, I can say that that's R3, or R3 is equal to 0, right? That's why a lot of times I don't even draw that one. Then had this P force been anything but vertical, had it been at an angle, then R3 would not have been 0. So we don't want to always get in the habit of leaving that out, but oftentimes it is 0. Then if I sum the forces in the vertical direction, setting that equal to 0, I can say that I have R1 acting up plus R2 acting up minus P that's acting down, right? One equation with two unknowns, presumably P would be known, but R1 and R2 aren't known. So I'm going to have to take a little time out from that. Sum the moments, maybe I'll sum the moments about the left-hand side, setting that equal to 0. So I have P times the distance L over 2 minus R2 times the distance L. So I can say that R2 is equal to P divided by 2, right? Which makes sense. I mean, if you were to, have some load here in the middle and you and your friend were going to carry this out, if this distance was the same, you'd both be carrying half the load, wouldn't you? You'd expect R1 and R2 to be just half of the load. Well, if you plug this then back in up here for R2, you can say, therefore, that R1 is equal to P over 2 also. Okay. So we usually go through that fairly fast. We spend a lot of time in that in statics. I'm not trying to say it's not important, but you should be pretty comfortable with that process by now. So we got to get the reactions. That's step number one. Very important. You got to get the reactions. You got to get them right. If you don't get the reactions right, it's hopeless from there. So then with that, I'm going to slice through this thing. I'm going to cut through it here, and I'm going to cut through it there. So I'll look at a couple of these, and I don't think I'll get a chance to finish this today, but I'll get it set up, and then you can finish it if you want. We'll finish it when we get together tomorrow. So I'm going to look at x between 0 and L over 2. So I'll have some reaction here that's going to be P over 2. This distance here is x. And I've got the shear down and the moment like this. Okay, and I only draw that. I mean, if I were to really draw this the way it should be, I would say at the end of the beam, we would have the shear going right down through there and the moment's right on top of it. I've separated them just for clarity's sake, but they're both happening simultaneously right at the end of the beam. Okay. Do I have anything else? I think that's it, isn't it? Okay, so I can go through that. I can come up with what the shear force is and what the bending moment is. I'll also have to look at x between L over 2 and L. And I can do that a couple different ways. I could continue on drawing the left-hand side, where I'm going to have the shear again down, the moment counterclockwise. I'd better put this load in there. There's P. This is going to be P divided by 2. This total distance is x, and there is L over 2, right? So here I will hopefully come up with, and you can head home and see and try and get these on your own, what is V and what is M, and then over here, what is V and what is M. And if you want to check this, you might say, well, I think there's an easier way. Yeah, you bet there's an easier way. Well, I don't know whether it's easier. Sometimes the algebra will bite you on this. But we could draw the right-hand side, where we would say that we would have the reaction, which is R2, which is also P divided by 2. I would have this distance now, which is very important, L minus X, is this distance here. And our deformation sign convention, we have to be very careful of that. We're now looking at the right-hand side, so I need to use this, shear up moment clockwise. So there's the shear, and there's the moment. And when I get the shear and the moment from this one, should it be the same as this? It had better be. Okay. So I guess spending some time on Google about radial engines and maybe playing with this is your assignment along with your homework, and also making sure you're ready for the quiz when we get together next time. Is that right? Take care till then. We'll pick up on this problem next time.